Okay, hey everybody. This is the second part of our discussion about functions. In this part, I want to talk about the relationship between a function and its graph. If you've seen graphs before, if you've dealt with this before, I think sometimes we end up forgetting the connection and we think of the graph of a function as just kind of a label we put on a picture. Here's an equation and here's the picture we assign to it. And while we may have seen where it comes from at some point, it's really easy to kind of let the relationship fade into the background. And I think that relationship is really important to remind us of. So this might be familiar, and if not, that's great. But if it is, that's great too. But I hope we can reinforce this idea and not let it kind of slip to the wayside. So when we talk about the graph of a function, it's just another way in which we can display functions, right? We've seen tables and coordinate pairs. Graphs are another way in which to display a function, right? And remember what a function is fundamentally. It's a rule, a set of instructions that, given some set of things, for our purposes, it'll be numbers. So you have a set of numbers we call the domain, and each one, the rule assigns a different number, exactly one other number from a set of numbers we call the range. Those may or may not be the same sets. So that's what a function is, right? And so sometimes we visualize or display the function as I have right here, f of x equals 3x plus 7, right? The rule is there. Take an input that we're calling x, we multiply it by 3 and add 7. In some ways, this is a great display because it's succinct. You can compute and find for any given x what its output is, all that sort of stuff. Another way that we can display a function is in a table, right? So if I just put in a couple of values, I won't take too long here. Let's just put in a couple of values. Like if I put in -2, we can evaluate the function and see that we get 1. Let's put in 0 to get 7. Let's do one more. If I put in 1, the output is 10. Oops. Okay, right? And so again, this has the advantage of we get to really explicitly see the assignment. The disadvantage is, I have 3 examples from this function. In this case, if we take the largest allowable domain, that's all the numbers, right? There's no number that we can't multiply by 3 and then add 7 to. And so our domain, unless we put some arbitrary restrictions on it, is all real numbers. And there's an infinite number of real numbers. And here I have a picture of, or a table of 3 of them, right? So this is sometimes great when you're trying to analyze some specific data or something like that. But it's pretty limiting for a lot of the functions we have. However, it's a good way to lead into a graph. Let's take an intermediary step. If I take all these inputs and outputs and think of them as coordinate pairs, right? So the convention is our input is written first, and the output is written second. And so here's 3 coordinates, right? And then we have a set of axes. And so hopefully you've seen this setup before. The horizontal axis, we often call the x-axis. I want to be just a little more general because we don't necessarily have to use x, though we typically will. But it's conventionally used to show the input, and the vertical axis is conventionally used to show the output. And what I mean by show is, well, let's look at this point, -2, 1. On our horizontal axis, 0 is right at the center, our origin. -2 means going back 2 units, so in the negative direction. And the 1 is a positive 1, so we're going up 1 unit. I'm just going to eyeball this. It won't be perfect. That's bugging me. It's not eyeballed well enough. That looks good. And that was the same spot. I don't know. I was misseeing things. All right. Our second coordinate point, 0, 7. That means don't move anywhere in the horizontal direction and go up 7 units. And then finally, 1, 10 means move 1 to the right in the horizontal direction and then 10 units up, right? And this is where we start to see this is the relationship of, we don't have the graph yet, but we're beginning to build the graph. But the relationship is here, that each one of these points is an input-output pair, right? Meaning that for this function, the horizontal coordinate, if you put the value of the horizontal coordinate into the function, the value of the vertical coordinate will come out. And if we kept doing this, right, we'd find more and more and more points, coordinate points that were input-output pairs for our function, and we would eventually see, let's see if I can actually draw this properly-ish, so I can get through them. Okay, well, we'll call that good enough. Maybe I'll move it just a little bit. There, that's the tool I need. So in any event, we're imagining we actually draw this line exactly through those points. So that's close enough. That the idea is each and every point on this line, if I pick any arbitrary point here, if its input is some value A, oh boy, something I hit. This is not enjoying. All right, sorry about that. If we pick any arbitrary point on this line, if its input is A, its output will be f of A. All right. Or I could write that as the x coordinate is some value A, then the y coordinate is going to be 3A plus 7, right? Those are equivalent statements. Any point not on the graph, this is not the case, right? That they don't have this pairing. So that is our fundamental idea about graphs. Let's take a look at a nicer picture of this. Right? So here is the same function. So we're looking at f of x is equal to 3x plus 7. These 4 points graphed are some of the same points I just did, and a couple other ones, right? And the same idea. You can see this table on the left-hand side giving input-output values. And if we continue to add values and connect them all together, what we find is that line that I had graphed, right? So it's not that when we have a linear function, right, something in the form mx plus b, that's assigned a line. It's that fundamental to having an equation of the form mx plus b, 3x plus 7 in this case, the fundamental, when you have this coordinate plane construction, it determines a line. There's no way not to have a line if you do the input-output pairs as the points on the graph, right? That's what shows up. We didn't decide that. We started with a line, started with a linear equation, and what shows up when we plot points is a line, right? Let's just look at a couple of others, right? So here's the function g of x equals the square root of x over 3. So the function is telling us to take an input, take its square root, and divide by 3. Let's think about domain for a second as long as we're here. Since we don't know how to take the square root of negative numbers, this function is only defined for values of x that are greater than or equal to 0, any non-negative numbers, right? Notice I put in this table a -1 in, and the computer spit back undefined, right? We're not doing complex numbers. That's a whole other thing. And so we can't do the square root of -1. But for these other values that are not negative, we see the outputs there, and here's the graph of these 3 points. Right? And if we were to continue graphing them, we'd get this. Oops. Let's change our scale here. So there's our, this is the square root function, or a version of the square root function. Notice a couple things. The graph begins at 0 and moves to the right. That is a demonstration of the domain, that we're not allowed to put in negative numbers. If you're familiar with quadratics, this is like a piece of a parabola but turned on its side, right? And that just shows us the relationship between square roots and parabolas. We'll talk more about that later in another video. The other thing to note is, this is kind of a side note too. It's not really about graphing, but I do want to point out that the square root is a function, and the square root only spits back positive numbers, right? And you see this graph only has y values that are positive. When you take the square root of a number, there really isn't a square root. So the square root of 9 is not the square roots of 9. There's more than one square root. There's a -3 and a +3. But we've decided we want to pick one of them to be kind of the principal value, and that's the positive one, right? One reason for that is that we want the square root to be a function. And remember, a function given an input has only one output. So given the input 9, the square root function spits back 3. If it was 3 or -3, or both of those answers, then it wouldn't be a function anymore. What we'd see, let's just add, right? The negative value, so I put a negative in front of that, we get the bottom half of that parabola turned on its side. But if I want those negative values, I have to specify that, right, by putting that negative there. This is another idea that we'll talk more about in another video, but visually we can see that if we had both sides, it's not a function because it doesn't pass what's called the vertical line test. If I draw a vertical line, it would intersect this graph in 2 points, which is a way of saying a single input has more than one output, so it can't be a function. But more on that later. Let's get back to looking at graphs. Here's h of x equals 1 over x plus 3. Same idea. You can plot some points. Here's 4 points. It's not very clear from those points if you're not familiar with the graph of the function of 1 over x. It's not really clear from these points what exactly is going on. But let's take a moment to talk about domain. We've already seen that when we have square roots, we have to consider the domain. We have to consider negative numbers and the fact that square roots can't deal with them. We have a similar situation here. When we have a fraction with a variable in it, in this case, we have our 1 over x, we know that denominators of fractions can't be 0, right? We don't have, division by 0 is not defined. Another way to say it is 0 doesn't have a reciprocal. And so our domain here is going to be everything else. Any other number we can take the reciprocal of, right? There's no number you can't take the reciprocal of other than 0. And so what we should expect to see in the graph is that at x equals 0, there's some kind of gap in the graph. So let's see what this looks like. So we just imagine plotting more and more points, and what we end up with is this function. Right, it looks like this, and you can see it's maybe not perfectly clear what's happening at x equals 0. That's our horizontal or our vertical axis. Let's get rid of our grid, maybe to make it easier to see. Right, the blue graph that seems to be kind of turning vertical as we approach there. If we are to zoom in, we will find that it never actually hits the axis, right? If it hit the axis, that would be a coordinate point on the vertical axis, which would have a coordinate of an x coordinate of 0, a horizontal coordinate of 0. But remember, the horizontal coordinates, the first coordinate is the input, and we said 0 can't be an input. So this graph cannot have an intersection with this vertical axis because that would imply we get an output value when we input 0, which we can't get with this function. Right? But what happens instead is, if we look at the graph, we can get every value close to 0, right? There's all these tiny numbers close to 0. Those are fine. We can take those reciprocals. And what happens when you take the reciprocal of a tiny number? You get a really large number, right? The reciprocal of 1/2 is 2. The reciprocal of 1/10 is 10. The reciprocal of 1/1,000,000th, a really tiny number, is 1,000,000,000. And so that's why we see our graph getting really large there, right? The output values are really large on the right side of the vertical axis. The same thing happens on the left side. except they're negative numbers, so we get really, really large negative numbers. So, all right, there is our graph of that function. I want to revisit the idea of this vertical line test. This is the graph of an equation. It's similar to the graph of a function, but it's not necessarily a function. For instance, this is the graph of the equation x squared plus y squared equals 1. This is what's known as the unit circle. The unit circle, sorry, I lost my train of thought there. This is a graph of what's called the unit circle, just a circle that happens to have a radius of 1 and is centered at the origin, right? The graph of an equation is similar to the graph of a function in that each point on the graph is a coordinate pair where, in this case, the horizontal, the first coordinate is our x coordinate, the second coordinate is our y coordinate. If we put these values in for x and y in the equation's true, right? In this case, 0 squared plus 1 squared is equal to 1. And if you do that for another point here, for whatever negative 0.555 and 0.83185, or at least this will be approximately true because these are rounded decimal approximations, that they'll satisfy this equation, right? And this is true for all the points on this circle and not true for points off the circle. However, this is not a function, right? And let's just go ahead and see that with the idea of the vertical line test. Let's just put in x equals k. Let's try different. I think I have to be signed in for it to do what I want it to do. That's weird. Oh, I see why. I'm choosing letters that I'm using in other places to be things. So let's try. Huh. That is odd. Not quite sure why that's happening. Let me try one more thing. Let's get out of this. Huh. I don't know why it's not letting me make, but that's all right. We can get around this. Let's do the vertical line test by hand. So for example, here's a vertical line. Notice that it intersects the circle in two places, right? If this circle represented a function, then those two places where it intersects, right? So there's a point right here and a point right here. Let's get out of. These both have the same input coordinate, right? And if it were a function, then the other coordinate should be an output. But we can see very clearly that these outputs are not the same, right? One is a positive value in this case, and one's a negative value. Even if they were both positive, it doesn't matter though. They're not the same, right? They're not the same. And so that would mean the input A has two outputs, whatever f of A up here is and whatever f of A down here is. Two different outputs. So it can't be a function. And that's the heart of the vertical line test, right? That if there's any place where you can draw a vertical line of and the graph, if you have the graph of something you are wondering if it's a function, if there's anywhere where you can draw a vertical line that it intersects the graph more than once, then you're not looking at a function. If there's nowhere where it intersects more than once, then the graph does represent some function, okay? And that is our vertical line test. Okay, I think that's going to be it for this one. I will we have a couple more topics in this function introduction section, but this is, I want to try to keep them shorter. So that's it for this one. I will see you next time.